So this is problem number 6 of the QHack 2023 Quantum Coding Challenges, and is entitled Hamiltonian Sandwich. And what we're being asked to do is to first implement a circuit where we're going to apply Hadamard gates to an arbitrary number of qubits. So we're not given exactly what the number is, so we need to leave the number of qubits as a parameter. And then we apply Hadamard gates everywhere. And then we perform measurements to calculate the expectation value of this Hamiltonian. So this Hamiltonian applies poly X operators to qubits that follow this condition where I has always to be smaller than j, and then applies poly Z operators on all qubits from 0 to n minus 1. So to clarify what this means, we can look at an example here. So for example, for n equal to 3, what we're going to do for the XX operators is we apply x to qubit 0 and qubit 1, because qubit 0 is smaller than 1. Then apply it to qubit 0 and qubit 2, because 0 is still smaller than 2. And then apply it to qubit 1 and qubit 2, because 1 is smaller than 2, right? And then for the poly Z operators, we just apply them to all qubits. And this will have a coefficient of -1, and the XX operators will have coefficient of 1/3. So let's go ahead and take a look how to do this in pennylane. So for this, we're going to use the QML Hamiltonian class in pennylane. But first, let's define a function to apply that Hamiltonian to an arbitrary number of qubits n. So I'm going to pass this parameter in here. And this Hamiltonian class requires two things. First, it needs the coefficients for each of the observables, and then the observables themselves. So we're going to create two empty lists, one for the coefficients and one for the observables. And then we're going to populate these lists by iterating through some for loops. So first, let's do the for loops for these XX observables. So the coefficient I has to go from 0 to n minus 1 here. Well, this will give me an iterator starting from 0, and the last one will be n minus 2. And the reason we will go only up to n minus 2 is because the jth coefficient will be the last applied. Then we need to iterate for the j coefficients, and those are going to go from I plus 1, right? So j is always larger than 1, so we only need to iterate over one number above where we are in I, and then up to n, which is the last qubit we'll have. So again, this iterator will go to n minus 1. So here we go to n minus 2, this goes to n minus 1. And then what we do is, to this coefficients list, we append a coefficient of 1/3 for those XX operators. And then to the observable list, we append the product of poly X observable on I and the poly X observable on J, right? And then we can do a separate for loop for our Z observables. So for I in range, and those go for all qubits, so up to from 0 to n minus 1. So we do range up to n, and then we append the coefficients for those Z observables. So we said they have coefficients of -1, and then to the observables we append QML poly Z on I, right? And then this function is going to return QML Hamiltonian, and we pass those coefficients and the observables. Okay, so let's maybe go ahead and just print what this returns if we pass, let's say, a value of 3. So we get this C observables with coefficient -1, and then x0, x1, x0, x2, x1, x2 with coefficient of a third, right? And if we do, for example, here 5, let's see if we can print that. We get all these different coefficients from z0 to z4, and then all possible combinations of xx operators where the ith coefficient is smaller than the jth coefficient, right? So here we can see we get the correct values. So now we've defined this function that would return the correct Hamiltonian. Next, we're going to create our circuit. So let's start with, let's say, a circuit that's going to have 8 qubits. And we define our device, as always, with a number of wires equal to the number of qubits. Create our Q node. And then the function, let's call it Qn Hamiltonian, or I don't know, something like that. Let's actually see what they use for the problem. They just call it expectation value. So let's call it expectation value, and it takes the number of qubits. And as we saw before, what we do is we apply Hadamard gates to all qubits, so we can make use of this function we saw before, broadcast QML Hadamard on wires equals n, and pattern equals single, right? And then all we need to do is just return the expectation value, sorry, QML expectation value, right, of the Hamiltonian we're creating, and pass the number of qubits again. Next, let's print our circuit. So let's do QML draw expectation value, and let's pass the number of qubits, and let's also print the output of that circuit. Let's actually just write down here xval, and instead of doing QML draw, we're just going to evaluate the function. Right, and we have a syntax error. I need a comma here, and here I should have done range n, because we want to apply that Hadamard to all the wires. So n is just a number here, so we need to pass an iterator that has all the possible qubits. And here we have it, and then we get an expectation value of 9.33. And if we go here, I use the number of qubits that it's given to us for this test case. So for the test case, we're given a n of 8, and we get an expectation value of 9.33, which is exactly what we got here. So we see that we've implemented the circuit correctly. So I hope that was helpful. Let me know if you have any questions.